So, hi everyone, welcome to the 6th Quantum Debate Colloquium. I'm Joe Brack, here from the quantum computing team at Frankfurt. And so I'm here to guide you through today's colloquium. So last year, Quantum Debate was kicked off as a state initiative for quantum activities in the region of Baden-Württemberg, to pull all these competencies and to create an overarching umbrella that further strengthens these networks and makes them more visible. So with this colloquium, what we want is to further promote this scientific exchange on quantum hardware, but also on algorithmic topics in the fields of quantum computing. And it's, yes, today I have the honor to present Dr. Christian Marciniak. I hope I'm not butchering.
No, very good.
Okay. From the University of Innsbruck. So he started studying his bachelor's at the University of Berlin, where he worked in precision metrology with optical resonators in Athens, Innsbruck, and he did his PhD with Michael Birkut at the University of Sydney's Quantum Control Laboratory, where he worked on design and operation of Penning-Eintracht for quantum simulation. And in 2020, before the pandemic, he moved to Innsbruck. Months group at the University of Innsbruck as a postdoc in the newly starting action experiment, which is one of the EU's Horizon 2020 quantum flagship programs. And he's now, and has since been the team lead at Action. And so Action focuses on quantum error correction, quantum characterization, verification, and validation, and also had some projects in quantum metrology, optimization, cryptography, chemistry, and even more. So today he'll introduce us to trapped ions for quantum information processing. Right? So yeah, any questions can be posted in the chat, and I'll give the floor to you for the presentation.
Thank you. I've been asked to project a little for the microphone, so I'll be talking a bit boomingly. I hope that doesn't scare you away. My name is Christian, as you've heard, I'm very happy to introduce. I'd like to thank you for having me here. And I am, as was mentioned, from the University of Innsbruck, where me and my team are operating and maintaining the new flagship quantum computer called Action. Now, it'll be my pleasure today to tell you about quantum information processing with trapped ions. I'll be talking about state-of-the-art perspectives and applications, and our device in Innsbruck is Action device. In Innsbruck, we have, and I'm saying we as a group, not me personally, of course, done quantum information processing with trapped ions for a quarter century now. In fact, it's where the first entangling gate in the world was done. And over that time, we have accumulated a wide array of different sorts of applications. I've listed a few of them here. And we've also been very fortunate in that we could acquire funding from a wide array of different sources, for example, national, Austria-wide, EU-wide, notably the quantum flagships, Action and now Millennium, and also money from the United States as part of some international collaborations. Now, as I've mentioned, I will be giving my talk in 3 parts. At first, I'll be talking about state-of-the-art and then some perspectives, and I'll be spending roughly half my time on that. And then in the second half, I will be talking about the recent application we've had, which is Steane quantum error correction. Now, I will start by giving you a sort of broad overview of trapped ion technology, in particular in view of quantum information processing. And I'll start very high level with the sorts of capabilities that we have, and then I'll talk a little bit more technical. So to start you out, I have here this map. And I should say that nothing that I'll be saying today is claimed and intended to be exhaustive, neither in people doing it nor in scope. But here is something shy of 120 pins of academic groups in the world working in trapped ions. And I know this list isn't exhaustive because there's a couple of dots missing here. This isn't political, they just haven't been updated. But I think the general gist comes across that there's a lot of people in the world that are working on trapped ions. And with this rising interest in quantum technologies, of course, there are also now commercial players And I have added here the logos of all the trapped iron hardware ones that I could think of. Maybe there's some missing. And there are definitely companies missing if I were to include soft and firmware that could be servicing this environment as well. And now looking at all of these people and all of these topics that they do, the question arises, why trapped irons? And also, at least for the commercial ones, we can ask, how did they manage to convince investors to give them millions, tens or hundreds of millions in funding? And I would argue trapped irons have a lot of things going for them. And one of them is that we have many decades and arguably a century of atomic physics and atomic technology that we can build on. And of course, that's not coincidence, because where atomic physics and metrology and what later became quantum information processing originate, this is all the same piece. The next thing is that atoms are natural quantum systems, and they are therefore perfectly identical always. This is a benefit if you consider that you don't have to deal with production variations. And then they also, oh, that's very well, anyway, it's a perfectly isolated system, or at least an extreme degree of isolation. They sit in the dark in some vacuum chamber, and they are surrounded by unfathomably low pressures. But still, because of the strong Coulomb interaction, they still are a strongly coupled system. And from this coupling arise some of the hallmark features that trapped ions have done for themselves. Now I have here, to answer the question that you may pose, how do they relate to other matter qubits late 18? Now I will preface this by saying that assessing the performance of quantum computers is hard. In fact, it's very hard. And so no single benchmark should be used to compare them. And in fact, even a lengthy list of actually ever give you, indications for trends and things to work on. These are also, at least for the most part, judgment calls that I'm making. But with all of this said, let's have a look at this list that I've compiled. And I'll start, it's all mathematics, and I'd say these are top contenders, so it's not an exhaustive list, of course. And I would say that it's pretty clear that superconductors in terms of data rate are beating everyone by a lot. Ions take sort of a middling position, and at least right now, cold atoms are rather slow, although they, I know that they're working to improve this substantially right now. But trapped ions have very high operational fidelities, and they always have been very high. You can say that both cold atoms and superconductors also have high fidelities, and I've made this qualification here that for superconductors, this is possible due to the ubiquitous and ingenious use of optimal control techniques. This is something I will be getting back to in a little while. Trapped ions also have remarkably low span, so that's state preparation and measurement error, and they have this all-to-all connectivity that can be beneficial for many applications, right? But the thing that's sticking out as a sore thumb is the register size. Now, anyone who is worth their salt in quantum should know that register size on its own is a terrible measure for capacity. Otherwise, D-Wave would have, won 10 years ago or 20 years ago with the 250,000. But it's certainly a near-term challenge that the ion community has to address, and perhaps more than other top contenders, although, it remains to be seen whether all the claims of scalability in other platforms actually pan out the way they are envisioned. But it's certainly something that we have to address reasonably soon. And now we have to do this in a way that we maintain all the things that we know and love about trapped ions. Let me tell you about some of the capabilities that we wish to maintain as we scale the register size. And as I've mentioned, we have a natural atom platform, or ions, that we encode information in. And atoms are shockingly not two-level systems. And we have worked for many years to develop techniques and technologies to make atoms be describable as two-level systems. But in the, say, last 5 years or so, there has been a change of mindset where rather than looking at them as nuisance, we have realized that these other levels actually can be used to benefit. And I'll be using this nomenclature of the somewhat provocatively named OMG proposal to describe this, in that I'm saying that within the same atom, I can encode my quantum information in different ways. For example, I can be using an optical transition I could be using a metastable where neither of the states that I use to encode information are actually the ground state, or I could be using ground state qubit. Depending on whether the nucleus has spin, it could be using a xenon qubit or a hyperfine. And I can connect all of these using narrowband optical quadrupole transitions, various types of Raman, or I could be using direct microwave dipole transitions. And another thing is that when we have all of these levels, I can also do other things with it. For example, I can go into a naturally qubit platform. Qubits are a relatively recent addition to the quantum toolbox, and they are very powerful because plenty of systems aren't two-dimensional to begin with, and we spend a lot of resource trying to make them qubitized. Or I could abandon this electronic structure altogether and just use the shared motional modes of ions in the trap that are there by virtue of the Coulomb interaction and encode my information in bosonic modes that are limited in number. When I do encode my information, let's say I'm doing this in an electronic state, I have to read out what this information is. And for trapped ions, this is usually given by the position or the occupation of a single valence electron in an atom. And it is gobsmacking that you can tell where a single valence electron is with incredible signal to noise. And when this was first shown, it made big waves, but it's still very much the foundation of the very good span that we have in trapped ions. Now, I've alluded to this several times already, but trapped ions are a hybrid system. It's a composite system. For a qubit, this is fermionic in the electronic, and then we have the bosonic modes of the trap that form a composite system. And in that composite system, I can do various operations to get benefit. I can drive, for example, different resonances, either on the carrier that doesn't interact with the motion, or on the sidebands where I do interact with the motion, and then that I can use to create electronic superpositions, interesting motional states, or I can produce and distribute entanglement. And with all of these different things for this hybrid system that were developed over the last decades, I now have a rich toolbox of things that I can do. For example, you have single qubit operations that are universal. They're usually implemented in the XY plane of the block sphere by resonant operations. So that's arbitrary angle, arbitrary axis in the XY. And then on top of that, I can use, for example, Z rotations, but what at least in processing is done frequently now is to use virtual rotations, like they would also be used in solid state systems. We have, of course, entanglement operations. They are usually, not always, mediated by the bosonic bus that the motion presents. That is pretty similar to conductors and the photons in their resonators do. And the most common ways of doing this are the Mohr-Sorensen interaction and optical dipole forces in the light shift gate. There are also some natural higher body interactions you can use in trapped ions. So not a two-body entanglement gate, but say three, which are currently being explored. Then I've already mentioned there's all these other levels that we can do non-qubit operations with. We have, for example, spectroscopic hiding, which is very useful. And then we have various, let's call them auxiliary operations or naturally qubit operations, like resetting qubits, possibly even mid-circuit, and other capabilities like mid-circuit net. And then one thing that is, I guess, unique to the atomic quantum systems is that the register itself, the amount of information carriers, the grouping, the position, this is all not fixed. It's reconfigurable and dynamic. And then using this toolbox, people have done many things in our group. I've highlighted a couple of projects, for example, quantum computing, error correction, quantum simulation, digital and analog, and optimal quantum metrology. Now the question to answer is, what makes an ion stay in a bit of space? Because the natural impulse would just be pick a direction, fly, and hit something, stick to it. And the answer is, of course, that we use an ion trap. I mean, it was in the title quite a while ago. There's different ways to do this, but the general gist is that I want to provide some sort of electromagnetic field configuration that provides a force for a charge to put into space, and for it to stay there, ideally indefinitely. And there is a very common one, the Paul trap archetypically depicted here. I have a set of pieces that keeps the ion from going in this direction. And I have a set of radio frequency electrodes that provide a potential that looks like a saddle. So confining one direction. But if I choose the parameters of my RF field correctly, then it's indicated here by a rotation should actually be flipping. The time average potential looks like a harmonic well in 3 directions. And so that will keep my ion steady. This isn't the only way to do this, it's just the most popular. There's another very popular one that has usually different applications, but the universe's best vacuum, for example, probably the penny trap at CERN. And penny traps use a static electric and a static magnetic field that are superimposed. If I have a charge moving in a magnetic field that experiences a Lorentz force, this is the international sign of the physicist. And then that leads to these very pretty epitrochoidal trajectories that you can see here. It's a fun word to say, epitrochoidal. And this is also stable, and if you use relativity, it's not stable indefinitely, but definitely long enough for us. And what you can see here are 2 archetypical, what we call maps that can trap a lot of ions, but we don't want ions, we want qubits or qubits, and we have to individually define and address ions to make qubits. And in a 3D trap, which is pretty large, or microscopic trap, so you can see by eye all the structures. If you can only define, a handful, maybe 100 qubits in that, that doesn't scale very well in terms of size. So people have thought, I could just project all of these electrodes onto some microstructured electrode, and then I can also get a 3D confining potential. So this is still 3-dimensional trapping, just that the electrode structure is 2-dimensional. And these things will then look very much similar to what you would expect from a solid-state quantum system. And now, with all of these things said, we are, it wouldn't surprise you if I said that it's not clear what the power is in quantum technology as a whole, and therefore also not for trapped ions. And therefore, there's this entire zoo of different things you can be doing with trapped ions for the same purpose. For example, we can be using Paul or penny traps. We could be describing macroscopic or microscopic traps. We could also make a distinction between traps that are 2-dimensional in their geometry or 3-dimensional. We could be talking about traps that are primarily using shuttling or addressing optically. And then even if I restrict myself to surface traps, I could be making the distinction between different ways of arranging and rearranging them. The very well-known quantum CCD architecture, for example, used by Quantinuum, originally from NIST, or the very recent work that we've done in Innsbruck on what we call the quantum spring array. Now, it is evidently impossible to talk about the present without mentioning the future, because a lot of the things that we do today are to solve problems that we will face tomorrow. And so I will now pivot to talk about the perspectives of the field. And the future is all about scaling. Now, I've mentioned there's no good single benchmark to describe something complex. If I could use a single number to describe something complex, it wouldn't be complex. But let me pick the very much imperfect measure of quantum volume to describe the progress of the field. Then I think it's uncontested to say that Quantinuum is leading, and by a long shot. This is a graph someone has made. It's not super recent. In fact, there are 36 or 32 roughly here. But even if I were to use that gradient over the last, say, 4 years, it's still not enough, because this axis here, we want to be at thousands, tens of thousands. So by extrapolating the current pace, that will take many decades. And we're probably not patient enough for that. So there are many challenges to surmount for us to pick up the pace. And these challenges aren't unique to trapped ions, of course, but I have picked a few here that I think are very relevant for ions and atoms. This list is not exhaustive, of course. And one of them is, how does this look like? This is also a problem that fixed arrays face, because you have to manufacture them a certain way. But we even have the of changing this. Should we change it? Then there's the question, how do I define and address qubits in such an array? And then also the very general question, let's assume I had a large-scale quantum computer that has tens of thousands of qubits. How do I control all the complexity inside? Because somehow there has to be control lines going to that. And then also this is potential, but almost certainly going to be required that we make quantum computers modular, and then they have to be somehow interconnected quantumly, not just with classical communication. So for registers, trap ions have used a large single potential well, and increasing the register size meant to just add an ion into that same potential well. And that brings with it a lot of technical problems. And to circumvent this, people have started using dynamic registers in, for example, this QCCD architecture, where you have unit cells of, say, 1 to 4 ions that you shuttle around and make interact. But when people did do this, I mean, it's performing exceedingly well. That's what Quantinuum is doing. But when they look at how much time they actually spent on quantum operations, it's not a lot. Right? So that's a problem. And that's not a Quantinuum-specific problem. That's what everyone is experiencing, that most of the time you're not actually doing quantum operations, you're shuttling and cooling. So there are different ways you can address this challenge. And in fact, people have looked at systematically in this publication, for example, at the trade-offs between shuttling a lot and the compounding technical problems from large registers. And it's now widely believed that the answer is to be something hybrid, where you have larger unit cells within which you still have your also connectivity and that don't require just excessive shuttling. There are here 2 examples of, let's call them complementary approaches, one from the University of Mainz and one from the University of Innsbruck. Both have connected subregisters of, let's say, roughly a small quantum error correcting code. And then within this, they have still their also connected. There are some very different approaches to this. I will highlight here from ETH Zurich. There's also this very new startup, also called Zurich, I guess, or Zurich Q, that is using microstructured penning traps that have different technical challenges that are possibly able to circumvent some of the bottlenecks, but this is very young still. Whatever way you organize a register, you still have the challenge that you have to address and identify and define your qubits. And that's typically, or like historically, been done using outside optics that are very large, bulky. And then you have usually some electro-optical or micro-electromechanical system that steers beams from the outside to the inside. There's 3 examples here from the University of Innsbruck, INQ, and also Quantinuum. But large bulky things don't tend to scale very well. So there are, unsurprisingly, again, different ways people are wanting to tackle this problem. For example, in Mainz, they are still using external scale big optics, but now at several light interaction zones, as they call it, so that they have a mix of shuttling and addressing in several sites to reduce the total overhead in shuttling. Many others are working in photonic integration directly into potentially a wafer now anyways. So I will highlight MIT Lincoln Labs, Sandia National Labs in the United States, again, also Infineon in Villach in Austria and in Germany, that are working on integrating waveguides and micromirrors and micro-optics, splitters, creating couplers, and also some active elements like modulators. And all of this poses very non-trivial material science problems. There's an entirely different way that people have also looked at this, and that was spearheaded by Christian Osbeckhaus during his time at NIST. He has moved since to Hannover, and he's now continuing this work at University of Hannover and also at PTB, where they use an entirely laser-free way of addressing. It's integrating microstructured antennae, if you want, that are using near-field microwaves to address ions. And then they use, similar to what superconductor people use, optimal control techniques to get rid of the effect on the non-addressed ions, or residual effect, because the wavelength of microwave is definitely bigger than the separation between ions in a microstructure. And this is a path that Oxford Ionics has been taking, and they've been very successful with this, at least it's not peer-reviewed yet, but I'm pretty confident. And they had 2 papers recently where they now claim to be world record holders in single and 2 qubit fidelity as well as span. And with all this integration going on, electrical and optical and the microstructuring with lots of segments, the question arises how all of this complexity inside is ever going to be controlled from the outside. And usually it is done like this, taking this drawing from this PRX quantum. It has, a number of DACs and lines and data rates and filters and so on that scale with the number of qubits. And if 10n filters doesn't scare you, it should. Because if n is like 10,000, that's just, we're going to use a nuclear-powered aircraft carrier's worth of money in RF generators, and that's not it. So people are working now on different strategies that have some fixed number of lines and filters and all the like. And then we'll have some in vacuum and almost certainly in cryo switching networks and multiplexing or demultiplexing networks. And so this is something that has a lot of overlap with solid state qubits and superconducting platforms. So we can expect some synergies there. People working on this in the trapped ion community are, among others, Clearotech and Infineon. But if I were to look for this in the gigahertz regime, I'm sure I would find many other companies. So where's this all going? And if you look at the roadmaps that academic partners and also commercial ventures are putting out, they all look pretty similar. You have your move to hybrid registers with shuttling, and then also integrating of photonics, and then in the not too far future, some form of probably photonic interconnect between different modules. And what I think is also quite striking is if you look at the roadmap for IBM, which is famously not using ions, they look pretty similar, except that the photonic integration is probably not quite as exciting for them. I realized as of yesterday, there's a new roadmap from Continuum. It goes a bit further, but I like this one because it has the technology and the privileges. So, with all of this said, I would like to switch gears and talk about a recent application that we've done in our machine, which is Steane quantum aerospace, a bit more physics and less technology, or I guess information science. But before I go into telling you exactly what I mean by this, I should motivate a bit more why we're doing this. And the idea is, of course, that we want to perform quantum computation, ideally indefinitely. And it appears today without any other possibility to do this is quantum error correction. And someone may come up with something else, but for now we don't know anything else. And the ultimate goal is, of course, fault tolerance. I would like my logical error rate PL to be some polynomial of physical error rate, and ideally this polynomial. So logical errors are rare. But if you just do quantum error correction, there's not per se guarantee that you will achieve this. Because we are entangling gates, and entangling gates can spread around errors. So if I'm just doing QEC, then it's almost certain that I'm just going to have a 1 here. So logical error rate is the same as physical error rate, probably with some terrible prefactor here. So that won't do. And so we will have to explicitly do fault-tolerant quantum error correction by designing our operations and codes in ways that adhere to fault-tolerant design principles. And I will be using stabilizer code in this example, and it might not be perfectly apparent to everyone what a stabilizer code is. And so for the purposes of this talk, there's only 3 things you need to know. The first is, if I have a state psi and an operator S, as is called a stabilizer, it doesn't do anything to psi. So it's just the +1 eigenvalue state to that operator. And the second is that I could specify my state psi by telling you 2 to the n complex valued parameters to fix it in Hilbert space, but I can also tell you exactly n stabilizers, and that does exactly the same. And this is usually depicted like this. There's Hilbert space, which is apparently blockular. And then every time I specify an operator, I remove a large part of Hilbert space that has the wrong eigenvalue. And if I keep doing this, I end up with a smaller and smaller volume. And if I do n-1 such specifications, I end up with just two states that I've already given the beautiful subscript L for logic. And then the third thing you need to know for this is that getting the syndrome, that is the information whether an error has occurred and ideally what and where, boils down to just checking the stabilizers. So if all stabilizers are +1, nothing bad has happened. Doesn't mean nothing has happened, we just don't care. And if at least one isn't 1, then something bad has happened, and hopefully I can tell what it was and where it is. So specifically, we've been using the 713 color code. It's a 2D code. It's also called the Steane code, which is a name that keeps coming up now. It encodes 1 logical qubit and 7 physical and has a distance of 3, which means that it can correct 1 arbitrary single qubit error. And it's a pretty nice code for a couple of different reasons. One, it's small, so we can do it now. It's also a Calderbank Shor Steane code. Again, keeps coming up. In fact, these two names will be coming up a lot now. So that means that the stabilizers, which I've written here for you, they group into all X's and all Z's. The Clifford group is entirely transversal, including the CNOT, which means that if I want to do a transversal gate, that will never connect 2 qubits of the same code, so it doesn't allow for errors to proliferate. And we will be using this transversal property extensively in what we're doing. And I just wanted to hammer down on this notion that checking the syndrome is the same as checking stabilizers by giving you one example. So let's say I have a bit flip error on bit 5. That will change the sign of these two stabilizers. Stabilizers that are affected, so I know exactly what the error was and where it was. I can apply a correction, and all is good. There could double X error at the same time gives me exactly the same syndrome. I would incorrectly assume that it was an X flip here, apply a correction, which makes it now 3 errors, logical error, error. And that doesn't contradict each other because all we've said is that we are going to make this code using fault-tolerant principles into p-squared scaling. This is already p-squared, p being the physical error rate, so it's all good. We increase the distance, it won't be good anymore. Now, in previous work, we've already shown that using the machinery of fault tolerance, you can improve state preparation in gates. So we've been using what's called flag fault tolerance, where you add some extra qubits and some gates that connect the ancillas and the data qubits in such a way that if an error occurs that I wouldn't catch otherwise, the flag goes up, I discard this run. And so despite the fact that this is more stuff than not doing it, we could show that the preparation fidelity of the states actually goes up. So the amount of errors goes down despite the fact that I'm using more qubits and more gates. But we won't just do state and gates. We also have to do parity checks, so read out the stabilizers, and we will probably have to do this very often if we want to do error correction. And so if we don't do this fault tolerantly, then the entire thing is going down the drain. There are a couple of different ways you can go about this. The most common way right now is what's called Shor error correction, where you use, for example, by flags, some fault-tolerant physical ancillas that I map my stabilizers to and I can read them out. And we are here using something that Steane proposed many, many years ago, where you use a logical ancilla. And I'll be going through how both of these work very briefly. So here's a circuit. If you look at it and think it's scary and unintelligible, I'm totally with you, because this is not a circuit that's made to be educational. One. If you're super astute and still awake, then you might notice that there are only 6 ancillas. That's the same amount of stabilizers, so there are no flags, apparently. And there's an entire section in this paper about a very smart way to interconnect the ancillas so that they flag each other. And this is possible because in Shor style quantum error correction, if anything goes wrong, I have to remeasure the stabilizers. I don't care whether it was the flags or the syndrome that was wrong. If this happens, I have to remeasure it again. And because we have a distance 3 code, we assume there's only one error that ever happens. If it did happen, its budget's already gone, so I can just remeasure the stabilizers without flags. And this number of times that I have to remeasure to remain fault tolerant actually scales with the distance of the code. So a larger distance code, adapting for more errors, would require ever more repeating stabilizer measurements. Measurements aren't free. And so this is what's motivated people to look into what is very recently, I guess, started to be called one-shot error correction. And Steane is one type of that. I think Quantino had an archive paper about tesseract code that's also one-shot. Let's look at Steane. And as I said, it uses a logical element. So that's a second copy of the same code that's already fault-tolerant by construction. And then we use this transversal gate property of the code that's facilitated by the ball-to-all connectivity in ions to connect them with the minimal amount of CNOTs possible. So very few avenues of error spreading between the two registers. And then different to Shore, we also don't map stabilizers individually to ancilla qubits because we only have one. But we will be getting the stabilizers by looking at the correlations between measurement outcomes in that one ancilla. This code, like all the one-shot quantum error correcting codes, doesn't have to be repeatedly measured in their stabilizers to remain fault tolerant. So that's great, at least if the error rates are high. And as I said, it connects the two registers with a minimal amount of CNOTs, which are also quite error-prone in these devices. So the machine we have done just this protocol on is the action device that I mentioned earlier. This is the, let's call it cheat sheet. You've seen a lot of these things before. We have the typical things in ions like a single qubit addressing, single qubit operations that are arbitrary. We use the Morma-Sorensen entanglement gate that's addressed. Yada, yada, yada. You can all look this up in this publication down here, which we've done quite a few years ago. But one thing to highlight is that within action, we had a particular eye on automated operation. Because the idea is in the future, you don't want a quantum computer to be operated by a little army of PhD students. It's supposed to be operating in a data center somewhere and running without human intervention. And so we've had an eye on automated tune-up and maintenance. There's a couple of technical details I won't be going through, but one I want to highlight. We have a duty cycle of somewhat north of 80%. So there's continuous calibrations running. If there's a measurement, it just stops, does the calibration, continues the measurement, all without you doing. And I think 80% is pretty good, considering that there's a lot of calibrating to do on large registers. And so this desire to go into a data center also motivated the form factor. We have this modular system and replaceable parts. There's a reasonably large team for an academic venture that's changing over the years, but it had me for a long time now. We have a new postdoc started last week. We have some very talented PhD students, some of which are looking for work soon. And we have a good master student who's hopefully going to stay. Now, this is what it looked like when we assembled it in the midst of the Corona pandemic. There's a couple of names here that you probably know. Athos, now I think is also part of the quantum Baden-Württemberg. And the trap itself sits in this little drawer down here. This drawer is unfortunately very, very full. So if I take a picture, it's just a mess of cables and stuff. So I'm using CAD here where I can make things invisible without breaking it. The general gist is that we have a vacuum chamber that's surrounded by an onion of other things. So probably not too illuminating, so I'll just move on and tell you about the results. What happened when we actually did run Steane error correction on this. And what you can see here is the logical fidelity of half rounds of Steane error correction, half because we are either doing the Z stabilizers in purple or the X, so we can compare them. And then we do this entire machinery repeatedly. So we have dark colors and light for experimental. And then when you look at the logical fidelity, it decays, unsurprisingly, with a number of rounds, and the purple ones decay. This is due to a very annoying technical noise that we have in our lab that we are going to get rid of very, very soon. But as I'm taking this measure, how it was, and so this is why they're not decaying at equal rates. And then once we've established this, we can also look into comparing full rounds of error correction between the two different paradigms, Shor and Steane. And here are again the circuits as a reminder for Steane and Shor. And remember that you have to repeat this every time there's a non-trivial syndrome. And so now the different colors are Steane in orange and the flat-based Shor in purple. And the top is the zero initial state and the bottom the plus initial state. And at the very least for zero, so that's not suffering from this access to phasing during idling times, we can say that Steane outperforms Shor. Maybe this is not surprising because, as I said, you have to repeatedly measure in case anything goes wrong in Shor, and it requires mid-circuit measurement. Mid-circuit measurement is a capability that's pretty new to us and the entire community. And like everyone else, we struggle with it, but this isn't a state that is anticipated to last. It's new, we got to get figured it out. But then, relatively soon, we are expected to be again in the situation where our error rates are dominated by 2-qubit errors or n-qubit errors. And so we've done a numerical study where we looked at, let's assume all errors are fixed at a low value except for the 2-qubit error, which is larger, and then we vary this. How is this performance going to change? Well, now only light colors because of experiment. And what we found is that Steane outperforms Shor by roughly about a factor of 2 in the parameters that we've chosen. And this is because you have to repeatedly measure in Shor. Now, if you keep reducing the error rate, evidently everything will converge to the same point, no errors. But there's probably also going to be crossover where Shor outperforms Steane because if errors are super rare, most of the time you don't have to remeasure stabilizers. And the average number of C-naughts in Shor is actually a bit smaller than in Steane. But this isn't too far, but also not too close. Sort of midway feature. Now, the last thing that I wanted to tell you about is that you can, of course, also do this on other codes, at the very least on all CSS codes. So we've just taken the simplest one, or ones, which are the repetition codes. They're not full quantum error correcting codes, so you have one for bit flips and one for phase flips. This one because of that phasing error I've mentioned. And I have the structure of the stabilizers here and also what the circuit looks like. And the two colors are now for two different distances. So for the orange, it's distance 3, and for 5, it's distance, for purple, it's distance 5. So that's more qubits and more gates. And you will notice that the one with a larger overhead actually performs better, which is the hallmark of operating below the threshold. Now, you could ask, why isn't there graphs for Shor? And the answer is very simple. As I've mentioned before, when you increase the distance in Shor, you have to remeasure stabilizers more frequently if anything goes wrong. It's already a challenge for distance 3. There's no question who's going to win for distance 5. This is because of this mid-circuit measurement error. If this is reduced, that will change. All right, and with this, I think I'm perfect in wrapping up my talk. This work that I've presented was done as part of a very large team of around 60 people. This is Reiner's, it's called Supergroup or Empire. This is various different groups that are culturally under this umbrella, let's say. We're also fortunate to have funding agencies all over the world and long-standing very fruitful collaborations with theorists that span the globe. And with that, I'm at the end of my talk, and I'm happy for your questions.
Thank you so much for the talk. It was very interesting. And yeah, so essentially now the stage is open for any questions. Also, the audience on YouTube can post questions in the chat.
I think you mentioned already, but what's the connection between Steane code and ions in particular? I think they lend themselves to this particular code, but you mentioned it, I didn't get it, so maybe it can repeat.
So the structure of the Steane code is very favorable for all-to-all connectivity. Like the way I have here. If you don't have all-to-all connectivity, there's a lot of swapping here. So that's basically the thing. The surface code, for example, where you only have nearest neighbor connections, offers itself to some fixed grid-like structure. Heavy hexagon is optimized for the structure that you have in, say, the IBM. If you wanted to do this, you can do all of these in all of the platforms, but no swapping. No. That's generally the gist of why we like that particular code.
Yeah, I would have a question regarding timescales. So in the beginning, you said ions have currently like kilohertz. Then during the talk, you talked about gigahertz scaling in the gates. I don't know if this is like...
That was the frequency of the radiation, not the repetition rate of the experiment.
Okay.
So we are using optical as hundreds of terahertz, right? So if you wanted to do Raman, that would be 2 optical or UV lasers where the difference is gigahertz, which is the spacing, but you can just bridge that spacing directly with gigahertz. That's the idea.
And then you obviously here also, you want to get rid of a lot of measurements, but we talked about mid-circuit measurements and that you can run those with a lot of measurements. So these kilohertz are gate times, I guess, right? For experimental repetitions, but what's the readout frequency, or what's the time for a readout?
Yeah, that's already in that. So a readout can be depending on whether you have an FPGA engineer or not. Let's say 100 microseconds and 1 to 2 milliseconds. This is actually a big challenge in the community. We are typically using EMCCDs, so electron multiplied CCD cameras, and the readout of the chip itself can actually be quite fast in the hundreds of microseconds, but it requires you to get your hands actually on the chip, and FPGA engineers could be paid much better not at the university. So Jonathan Holm has some very capable with a standard Android chip that can be very fast. For all of those that don't have some that it's in milliseconds. There are some cameras that can be faster, like out of the box, but that's currently still in development / the commercialization. Yeah.
Okay, and so maybe one last question in the direction of those frequencies. So for applying those fault-tolerant and for narrow correction, that makes perfect sense also from the architecture. Now we tried also to use those systems for quantum machine learning, which clashes a bit with kilohertz frequency.
I agree.
So how do you expect the suitability of those devices for such algorithms?
I mean, it might not be very popular, but I don't think quantum machine learning is suited as long as the data rates are so small, right? Yeah, I don't know whether you class variational quantum algorithms into that also, but there are, and in fact, we very recently put out a quantum chemistry paper where I was hesitant about them doing VQA on the machine, but it turned out to be very resource efficient. So it depends a lot on how exactly you do it. If you're not cognizant of that data rate, then it's going to just drift away and you're never going to converge to anything. Data rate is nice. If you have high data, but also very fast decoherence, then you can produce a lot of very bad data, and it's also going to produce problems. So I would say, like classical machine learning on quantum data in that 2x2 matrix, that's something that can be very gainfully applied right now. Quantum machine learning of quantum data is future. But the kilohertz data rate is a problem, right? And the hertz data rate is a big problem. And if we ever want to, still use this general, I can get an answer within a few hours, maybe days, sort of mindset that we have right now, this has to change. Maybe it won't change, and very important questions will just take months. Also possible.
I can also ask the question. So also related to this application-wise, do you have a feeling for what in near term or maybe mid-term applications ion trap quantum computers would be most useful for, and how they compare with other quantum technology?
Application, I assume you mean like industrial or?
Yeah, also.
Right. Difficult question, especially now that people have commercial interest in the answering of such questions. I mean, as an academic, I would say not for a long time. But then you have companies like Quantinuum and many others saying, claiming they are doing something useful for their partners. I'm not sure. I mean, I can always pick a metric to define useful, right? You can certainly be useful for academic purposes right now. And also, I think what is often underestimated is we are doing computation. We're not the first to do computation. There's a whole discipline, computer science, that is also doing quantum computation. And I think they're often disgruntled by us claiming we're better than them. And so I quite like to see when someone comes out like, this is the fastest computation anyone's ever done. No classical computer can beat this. And 2 days later, someone has dug out an old Atari and they made a better algorithm, right? So I would say there's certainly utility in that you keep the computer scientists on their toes of finding either better classical algorithms just to spite us or quantum-inspired classical algorithms, right? So that's certainly something. And then, of course, we learn a lot about physics. We learn a lot about material science that has wider applications. For the immediate benefit, I would say sensing is actually going to be first to provide actual utility. A few examples were quantum metrology, not just quantum enhanced, but actually quantum metrology is already better than best classical. And that's usually in a situation where, for some reason, classical resources can no longer be expanded. So, for example, there's a nice Nature paper from the University of Brisbane, or in Brisbane, University of Queensland, where they do life science microscopy. There's this very well-known limit. If you keep increasing intensity, the resolution increases, but also the amount of light that is sent onto a sample, and at some point it's dead, which you don't want. And so then you can use entangled photons to beat that limit. Right? So if there's a hard limit for some reason, that limit could be imposed by physics or your budget or whatever, then quantum can actually provide a tangible benefit right now.
What about in the long term? What do you see, let's say, high-impact quantum computers, like you see a specific set of problems where they would likely excel in comparison to other types of quantum computers?
Not necessarily. I mean, I could, wager something right now, but I mean, that field is as old as my academic career. It's not very long. So, and I didn't see any of this coming. I mean, again, in sensing, perhaps clocks, but then, there's always this back and forth whether currently there's a co-reactive clock or a time clock that's best, but that's something that's very well suited for. For computation, it has its benefits, but it also has its drawbacks.
A bunch of questions.
Yeah, thank you for a nice talk. So you mentioned problems with the scalability in terms of, the apparatus which you want to use to control qubits, for example, lasers. So there's this company you also mentioned, this Electron from Germany, which tries to use radio frequencies and play with magnetic fields. So could you tell, what are the benefits of this, and is this promising? If you have
well, I'm not going to the slide. Oxford Ionics uses the same approach, right? And as I said, that's it comes out from Christian Ospithaus, who already had this idea back in his postdoc times at NIST. And I mean, it says laser-free addressing. It's not free of lasers. You still need lasers for state preparation and cooling. And I didn't mention this, but the laser cooling is what gives us access to temperatures much, much colder than what a dilution refrigerator can do, right? But you get rid of the very nasty, super stable lasers. And the idea is to drive these magnetic dipole transitions directly. The sort of challenge that you have there is the wavelength. Right? The idea of directly addressing the dipole transitions is not new. I've done this in my PhD as well with a horn from the outside, but then you just irradiate everything and then you have 1 qubit. I can do 1 qubit on a piece of paper. So what they're doing is integrating sort of for example, meandering electrodes directly onto the trap, and then have a combination of magnetic field gradient and these microwave fields that directly drive that transition. Now, the challenge is that you have to make sure that the other ions aren't just seeing exactly the same thing. But the benefit is you get rid of that very difficult laser. And also, this is electronic integration, and we have an entire industry dedicated to that. So that's the beauty, right? I think that is very promising. I don't want to be doing it, but I love reading.
Yeah, thank you.
Yeah, thanks for a great talk, very interesting. How do you couple these logical qubits? So you say there's 7 qubits, you need the all-to-all connectivity, all right? And if one logical, how do you couple this to another logical qubit? And do you have to shift around all the 7 qubits all the time for every like 2 qubit gate between logical ones?
Yeah, so this is all a single register. So we have 16 ions. We also need some ancillas, right? So it's 7 plus ancillas. And so because they share a single potential, well, we have all-to-all connectivity here. If you don't want to be doing this, and we have good reason not to want this, then you have to go to that slide, actually. Where is it? Always there we go. Then you have to think of something else, right? So people have this QCCD architecture where you have storage zones and interaction zones and so on. You could be bringing them together, for example, or you split and merge. With large crystals, going through the junctions is very difficult because the junctions are field free, and so they can just heat up a lot. They're not going to escape, but they're going to heat up. There's some, for example, the spring array that we've recently had, where you have these blocks here, and then you can bring them together either radially or axially. And if you want, I don't know, this one with that one, we can just shift the entire thing back and forth. And you don't actually bring them into a single potential well, but into a double well like this. So they're still separated. And then you have dipole-dipole coupling. You can read all about this in that paper, for example. But the scaling of this coupling is actually not as bad as you would assume it might be. It's still going to be challenging to get good gate times, but this is like a few months ago, it was pretty decent. Otherwise, you will have to do shuttling. And there is an IARPA project running right now where different parties are looking into exactly this. Let's assume you have a module with one logical qubit, and you have a module with another logical qubit. How can I connect them without just smushing them together? Because there's also this question of how errors propagate and the richness of the error landscape if it gets too big. And one way you can do this, for example, is lattice surgery.
So that has reached the end of the talk. Thank you so much to Christian Marciniak for the great talk. And thank you to the audience, even at home. So the next block will be in 2 weeks, where we'll have Dr. Werner Dobhaus from Chalmers University of Technology, presenting their work on quantum chemistry simulations with the title Quantum Computing Meets Quantum Chemistry, Potential New Era Simulation Study. So we hope to see you then, and thank you for the attention, and have a nice afternoon.